organizer as well. So I'm really happy to be here. So today I will like to report on some recent joint work with Tom Mark, who is in the call here. Okay, so this talk will be about a set of questions and conjectures that sit at the intersection of simplex and contact topology on one side and complex function theory on the other, and it has some relevance to low-dimensional topology. A couple of the particular goals are that on the symplectic side, I'll talk about contact type hypersurfaces in R4 with the standard symplectic structure and try to understand its topology, the topology of such surfaces. And on the Stein side, complex side, we'll be talking about Stein domains in C2 with varying degree of convexity. And finally, I'd like to discuss and provide some new examples for a version of symplectic holomorphic rigidity in low dimensions. So as I said, this will be reporting on some recent work with Tom Mark, but there are some other people and results in the literature who also thought about this question and produced important results. Some of them were particularly influential on our, the way that we're thinking about these problems. And the nice thing is that our results and techniques will be quite complementary to what they did. So I think that's a nice thing. Okay, so let me start with maybe some motivations, in particular this kind of the classic problem, which asks which closed-oriented three-manifold Y embed smoothly in R4, and it doesn't matter if it embeds in R4, it will embed in S4 and vice versa. And just with some simple algebraic topology, you can see that actually many such don't embed in R4, just for reasons of homology. For example, length spaces never admit in R4. So just to kind of then maybe to avoid this kind of problems, let's just focus so-called integer homologous spheres. And when you do that, the situation suddenly get very positive because of this result of Friedman in topological category. Indeed, any such Y can be embedded in R4. Indeed, even better, any such Y bounds a constructible topological form manifold. On the other hand, on the smooth side, the problem is complicated and it's largely open. So what we will try to do today is we will impose additional geometric conditions on the embedding. In that case, the thinking, for example, R4 either with this standard symplectic structure or thinking of it as C2 complex structure there, and then think about getting maybe more uniform results via these extra conditions. So, and this is a goal. I will make it concrete by some results a bit later on. But there is a more like long-term goal here by imposing these additional geometric conditions, and it will be because of the following one. So the goal will be that hopefully getting some maybe more information about smooth form manifolds. So for example, if you look at these two results, if you put them together, you get an interesting smooth form manifold topology result, namely that you find closed form manifolds with no smooth structures. And in this contrast between the smooth category and topological category is very useful. And maybe one goal, long-term goal, is to use this kind of hopefully some results in with kind of more rich geometric structure around, we can get similar results. And if we have time at the end, I have a bonus slide. I will talk about one such idea for this goal. But for now, let's kind of look at this kind of part a little bit more in detail. In particular, I would like to start with some interesting examples for which we know that they embed in R4 smoothly. So this will be so-called mesotype manifolds. So here I drew for you a form manifold given by a single 0, 1, and 2 handle. So what we know about this form manifold is just easy calculation shows that it's indeed contractible. And the boundary of such manifolds could be really interesting. And boundary will be an integral homology sphere. And what is true about this is that not just the boundary, indeed the entire 4 manifold smoothly sits inside R4. And if you have never seen it, the proof is really nice. It's actually just original proof of Mazur's from 1961. Is that you thicken this 4 manifold, you cross it with interval. Now it's a 5 manifold, but the handle structure hasn't changed. Except though that now the 2 handle attached along this circle now attached along a knot in S1 cross S3. In particular, we can actually undo this crossing. So when you do that, indeed, this algebraic intersection 1 also becomes geometric intersection 1. In other words, 1 and 2 handle cancel each other, and this thickened manifold is nothing but 5 balls. And in particular, extend and embeds in S4 and hence in R4. So now, there wasn't really anything special about this attaching circle. It could be any knot as long as the algebraic intersection linking was plus or minus 1, things would be good. In other words, by kind of considering different attaching circles and framings referring to this N, we get various 3 manifolds for boundary of Xn. And typical examples we get are hyperbolic, but you also get Ciphered manifold examples. And many examples constructed like that start with some work of Atwood Kirby and Kassenherrer, Fintishaw Stern, and others. So what I would like to do next, just this Ciphered manifold examples will be particularly relevant for our talk today. I would like to talk about a kind of maybe some sense special class of Ciphered manifolds. These are so-called Briscoe homology spheres. So what you see here is that is like a Briscoe homology sphere sigma PQR, which is nothing but a link of singularity for this Briscoe singularity, a particular complex hypersurface singularity. Here we choose PQR to be pairwise relatively prime. That is what it makes them a homology sphere. If you don't choose it, so you will just get a rational homology sphere. And these spheres, they have an S1 action on them, which yields this Serger picture for them. Here, PQR as given and P prime, Q prime, R prime are some integers, could be arbitrary as long as they satisfy this condition. So, and you can generalize this. You can think about actually Briscoe homology spheres here. The picture you see is actually a picture of a Ciphered fiber space with 3 singular fibers. But you can generalize that. You can think about those that they have n singular fibers, and again there will be one singular equation that is A1s and AIs and the denominators need to satisfy. So as this picture suggests, and the same is true for general Briscoe spheres, they are Ciphered fiber spaces. And not just that, if you focus on the Ciphered homology spheres, they are indeed Briscoe spheres up to orientation. Okay, so this really encompasses all the Ciphered homology spheres if you wish, if you include orientation. Okay, so now these are some class of 3 manifolds, as I said, arise as the boundary of for example, Mazur type manifolds, and certain members there, they embed in R4 smoothly. Now I also want to talk about some restriction on smooth embedding problem. So the observation is that if you have a 3 manifold which embeds in R4 smoothly, then such a Y will bound an integer homology bond. And then you might be interested to kind of obstruct this embedding. You could think about a bit harder problem, namely try to obstruct a given 3 manifold to bound an integer homology bond. So, and indeed, this is exactly how you can use, for example, Rocklin invariant to, for example, prevent Poincare homology sphere to embed in R4 smoothly. And in our notation in the previous slide, this sigma Poincare sphere is nothing but sigma 235. And this kind of finding, like homology cobordism invariance, is kind of very popular even today. So, for example, integer lift of Rocklin invariant was introduced by Monolasco, this so-called the pin2 invariant. It also kind of shows many infinite families of Briscoe spheres, for example, don't bound integer homology balls. There is an invariant of, again, Briskman spheres developed by Tosun derived from gauge theory. And there are many more invariants, like various other invariants coming from Floer theories and gauge theories. So and one interesting conjecture I want to list is this is a conjecture can be found in a paper of Collar from 2006, that if you think about the Briskman sphere sigma a1 through an, that the conjecture is that this will never be a boundary of an integer homology ball if n is greater than 3. And as far as I know, we have no partial progress towards resolving this conjecture. So anyhow, so the message, I guess, is that the situation for smooth embedding question is rather complicated. And even if you restrict Ciphered manifold, the situation is still complicated. So then our idea is that we will try to make progress by asking embeddings that satisfy some version of convexity. So we will think two such embeddings. On the complex side, we will think about holomorphic convexity. In other words, we will ask why that embed in C2 in a way that it bounds a Stein domain. And of course, as we will see, this Stein condition, it is a matter of some sort of convexity, and there could be various degree of convexity. And on the symplectic side, we will require instead of the Stein domain condition, we require that Y to be a contact type hypersurface in R4 with the standard symplectic structure. So, and in that case, the Y inside R4 with omega standard will bound what's called a symplectic convex domain. So so as we will see, this kind of of course the Stein manifolds and symplectic manifolds are related, but somehow we will just see that symplectic convexity is much more restricting than Stein condition or homomorphic convexity. Okay, so I guess now I would like to just briefly explain just maybe some notation what we know about this holomorphic convexity. So so we'll be talking about Stein manifolds. So remember, these are manifolds that meet proper holomorphic embedding in some complex affine space, necessarily non-compact, but we'll be interested, so-called Stein domains, their compact version, and like given a Stein manifold, like given a smooth, let's say, even dimensional manifold, asking when is it admitting a Stein structure is an important question, and we have a characterization for it. It is this result of Eliashberg, who says that essentially, as long as you have an almost complex structure and you have a nice handle description, namely no handles of index greater than m, half of the dimension of manifold, then you should be able to set a Stein structure on this manifold. And here I want to emphasize that this is the result that, like, abstractly setting a Stein structure on a manifold. And this result is true exactly like this if m is greater than 2, but when m is equal to 2, then you don't have to worry about almost complex structure, that's always there, but now there is an additional framing condition. Very good. So, but now we will not be quite interested in setting a Stein structure on a manifold abstractly, but we'll rather be interested a domain sitting inside C2 to be Stein with respect to this ambient complex structure. So that is kind of it's not at all obvious that it will be just a matter of setting an abstract Stein structure. So maybe before I move on, let me just give an example, because this will be later on helpful. So for example, I mean, we might think many examples of a Stein manifold, but maybe a non-example will be something like this. Maybe a non-example is that, think about S2 cross D2. So this is, for example, cannot be given a structure of a Stein manifold or Stein domain. It's original due to Eliashberg and maybe some joint work with Gromov, but maybe cleanest proof I know is that you just there's a version of adjunction equality for Stein domains, and that will, for example, say that homologically essential embedded sphere has to have self-intersection less than or equal to -2. But here we see one that with self-intersection 0. So anyhow, so we will be interested in domains that are sitting inside C2 and being Stein with respect to the complex structure from C2. And for that, luckily we have a result due to Klump. It's actually much general result, but I will just use a very special case of it. Namely, if W happen to be an integral homology ball, and then as long as it admits a Stein structure abstractly, the way that it satisfies this criteria here, and that it embeds in R4 smoothly, then indeed you can make W embed as a Stein domain in C2. Again, so it could be the case as okay, if you're missing one of these, you might not be able to achieve what you want to do. So, like just to give an example, like why this is non-trivial. So, like you might imagine that okay, I think about a 4-manifold that is obtained by attaching a 2 handle along a knot to the 4-ball, a 0 handle. So a picture like this, maybe. So this is my maybe 0 handle cartoon picture, and here I have a 2 handle, which is attached along a knot here. So there are so many ways you can make this picture Stein by choosing the attaching circle for the 2 handle to be correctly framed, so that this framing condition is satisfied. But such a picture, for example, can never, or such a 4-manifold can never be made Stein domain in C2. And the reason is that okay, if that was the case, first of all, the attaching circle has to be a slice knot. But then when that is the case, you can put together the core and that slice disk to get an essential sphere with self-intersection 0. Again, that's not possible. So this kind of being Stein inside C2 is a bit more restrictive. But anyways, we still can have examples of this. The key is that maybe you need to introduce 1 handles. And here's a kind of an example of the general example of this. You will remember this picture from previous slides. So this mesotype manifold. So for this one, as we just saw by Maser trick, we can always embed Xn this contractible manifold inside R4 smoothly. And so if you choose n to be less than -1, -2, or smaller, it's easy process to make this Xn Stein. And the reason for that, if you look at this attaching circle, you can make it Stein. And if you do so, you will find that maybe the first thing comes to mind if you try to fix the at cusps here and fix this crossing, you will find that the TB of the resulting Legendre is -1. So what you want for framing conditions so that this picture becomes Stein is that the framing should be TB -1 or smaller. So this is n less than -1 is to verify that. So hence, applying Gaume flexibility, we get that indeed this boundary of Xn does embed in C2 as the boundary of a Stein domain. So it's an interesting question. Well, what happens n is equal to -1? Well, first of all, if n is equal to -1, boundary of this contractile manifold is this Briscoe sphere sigma 2 313. This was explained by Abdul Kirby first, this was a result a few years ago. Tom and I proved that indeed this particular contractible manifold, when n is equal to -1, cannot be made Stein. So we had a slightly different motivation when we were trying to answer this question, but then in reality there is a kind of much deeper conjectural, prediction behind this result, which is this conjecture of Klump, who claims that indeed Briscoe homology sphere will never bound a Stein domain in C2, and he conjectures that this will be the case with either orientation. So this conjecture is still largely open. The only progress we have is this previous theorem I just said, and is that we also can verify this conjecture, or did verify this conjecture for this infinite family. So yeah, So this is kind of the maybe one conjecture that is still largely open, and it's about the holomorphic convexity. So now the other constraint one might be kind of interested to put on for an embedding problem is considering that, okay, or saying that, or asking that y to be a contact type hypersurface in this symplectic manifold. So in other words, y will be boundary of a symplectically convex domain. So the picture we should have in mind is something like this. Here we have our 4 with the standard symplectic structure. I'm sorry, my handwriting or style is nowhere close to how Angela did. So here you should think about this y, which is a codimension 1 submanifold. So here I guess this will be our w. And then what we require to be a contact type hypersurface is that, okay, you have this Liouville vector field transverse the boundary, and it is pointing out in this y boundary. So once we have this set up, then y will be a contact type hypersurface, and w will be a symplectically convex or convex feeling of y. So this is just essentially that, and maybe some examples of symplectically convex domains are fourfold, or the one handle, or various disk bundles studied by Nemirovsky and Siegel. So now I just want to say just a few things about how symplectic convexity and this holomorphic convexity maybe relate. So here is a kind of how I think about a holomorphic convexity or Stein domains inside a larger Stein manifold. So here, for example, X could be C2, and for phi you could take the square of modulus of Z, and then for J just take the usual complex multiplication by I. So here W will be a holomorphically convex domain in this X, Y, G. That means that I remember the complex structure from X, but maybe not the J convex function, not phi. What it is, this F is some J convex function available in some neighborhood of W. So now for such domains, or in general for Stein domains, you always have this kind of built into them Kähler form. And also on the boundary of such a domain, you have a contact structure gotten by the complex tangencies as such. And moreover, so this kind of, you can use this symplectic form to define a metric on such domains, and with respect to, if you take the gradient with respect to that metric of the J convex function, you get a Liouville vector field. So in other words, W is indeed symplectically convex with respect to this Kähler form here, omega F. But now, and maybe a warning is that even if even if omega is W is inside C2, the form omega F doesn't have to agree with the standard symplectic structure on C2. So in particular, boundary of W doesn't have to be a contact type hypersurface if it just bounds a holomorphically convex domain in C2. So now there is, but it's an interesting question to ask. When does this happen? Like, when can you indeed extend this Kähler form in the neighborhood of W to some Kähler form on C2? And this is precisely like the Stein domains that they have this kind of what's called they're rationally convex. So this rational convexity is a concept in quite studied and still popular in complex function theory. And these are type of domains where a version of Okaway principle holds, namely on such domains, holomorphic functions are uniformly approximated by rational functions. So for the definition, I will take the following theorem. This is, the first part is due to independent work of Duval, Svoni, and Nemirovsky, which is that indeed kind of domains that for which this omega F can be extended to a Kähler form on CM are precisely rationally convex domains. So take it as a definition if you wish. And indeed, it was remarked by Silibak and Liashberg that you can indeed take this Kähler form to be just the standard symplectic structure outside of a compact set. So these are what rationally convex domains are. And in particular, if you just think about so far, we have talked about, we had homomorphically convex domains, we have symplectically convex domains, and we have rationally convex domains. And here is how they kind of what kind of the implications going on here. So why is I'm focusing in the case where, again, we are looking three-manifold embedding in R4, but really all this could be changed, in particular this part, to taking R2M and thinking about codimension 1 embedding. So I guess these are the smooth questions we talked earlier, and this is symplectic convex part. This is the symplectic side, and here we have complex side where we are interested in the pseudo-convex domains, and here rationally convex one. So this rational convexity is kind of loosely at the intersection of this symplectic problem and complex problem. So now I think I'm ready to state some results. Results will be essentially thinking about can we kind of identify such Y's, whether they actually have, you know, symplectic convex embedding or arise as the contact type hypersurfaces or as like pseudo-convex domains, and also maybe say a little bit about whether we can reverse some of the implications or how they are related. Okay, so here is the first main result. So if you focus on Briscoe homology spheres, so we prove that indeed they will never arise as a contact type hypersurface in C2 or in R4 with the standard symplectic structure. And as a corollary, as a partial evidence, if you wish, for both Kolar conjectures and Ghom conjecture, we get that no Briscoe homology sphere bounds a rationally convex domain in C2. So these are the kind of the results. Essentially, if you will remember, for smooth question, the situation was really complicated. So, I mean, forget about general Briscoe spheres. The situation was really just kind of picking particular Briscoe sphere with the 3 singular fibers and just, you know, one at a time or like a small family. So here, there's a uniform answer that they will never embed as a contact type hypersurface in R4 or rational convex domain in C2. So here is some more results, and in particular, kind of maybe comparing this what is happening in higher dimensions. So you can think about this, you know, rational convexity or rational convex domain in CM as well. And this is a recent result of Silibak-Eliashberg. Indeed, if you're complex dimension 3 and above, holomorphic and rational convexity are equivalent notions. There is no distinction. And in particular, you can obtain many diffeomorphism class of contact type hypersurfaces in R2M with a standard symplectic structure. On the other hand, in dimension complex dimension 2, results of Nemirovsky-Segal and some more result of myself with Mark shows that indeed there are domains in C2 which are homomorphically convex but not rationally convex. So here are 2 such examples. Here is a single example. This was found by Nemirovsky-Segal. Let me call it NS. Why not? So this is a disk bundle over RP2 with Euler number -2. So, and what you see here is an infinite family of, and these are, if you look at it, is a contractible manifold. So Nemirovsky-Segal proved that this is, I mean, it's not very difficult to see. This is indeed holomorphically convex in C2, but it could not be made. You cannot make it rationally convex, and it just kind of essentially rests on this nice result that there cannot be Lagrangian Klein models in R4 with the standard symplectic structure. So, but for this example, these WNs, first of all, what you can do, because they are contractible, you can play out with this kind of the attaching circle. You can realize that no matter which n you choose, the TB is always 2. So with one stabilization, you can make it Stein, and then Ghom's flexibility applies. They are homomorphically convex in C2. But then we prove that they cannot be made rationally convex. So our technique, our kind of obstruction, interestingly, doesn't apply in Nemirovsky-Segal example. So it's interesting. But what we can say about Nemirovsky-Segal, Indeed, this Nemirovsky-Segal example is a special case of a kind of the much bigger infinite family, where for that family too, we kind of provide how all can be made holomorphically convex in C2. So, but now one corollary of this result, and this is true both for this Wn, but also for this Nemirovsky-Segal example, you can never, you wouldn't be able to isotope them to be symplectically convex domain in R4, and in a way that this isotopy that fixing the contact structure on the boundary. So in particular, you can't find a compatible Weinstein structure on Wn with Jn. Here Jn refers to this Steiner structures to build, and this again the same result for Nemirovsky-Segal example, that this sits symplectically in R4 with the standard symplectic structure. We do know that of course they have some Weinstein structure, indeed unique one, but just that they can't have one that sits symplectically in R4 with omega standard. Okay, so I think what I would like to do next then maybe just tell about how the proof goes. So what goes into obstructing Briskon spheres to embed as contact type hypersurfaces in R4, and also maybe explain how this goes. This example goes. Okay, so here are the steps of proof. So our input will be Floer theory. And even though we will primarily use Hegar-Floer theory, there is a part that we have to use an important result in monopole Floer homology. Without that, there is no way we can proceed. So the input will be, as I said, Floer theory. Here is how, just a little bit kind of the summary how things goes for a three manifold. As you will remember, there are so-called Hegar-Floer groups or monopole Floer groups, and if you have a contact structure, there is an invariant associated to so-called the contact class, and if W is a symplectic convex and on the boundary of Y, then you will find a contact structure, and this contact structure in particular will have non-zero contact class. So now the first theorem that we will prove is that indeed, if your domain is symplectically convex in R4, then the contact class has to be in the image of the HF infinity into HF plus. So another way to say it that this contact class, so for HF plus, it has this finite dimensional piece, so-called the reduced homology. So what this theorem essentially saying, what is it equivalent to? It says that this contact class got to be zero in the reduced homology. So that is a theorem. So in particular, this is our obstruction to contact type embedding in R4. So okay, so if we prove that indeed for a three manifold at hand we have, if the contact class that this hypothetical class contact class, this contact class coming from this hypothetical contact structure from the symplectic convex filling, if it is indeed non-zero in the reduced homology, then that cannot exist. That's symplectic convex filling. So let's see how this proof goes. So proof of this theorem. So consider this W symplectic convex domain in R4, and take a large ball that W sits is interior. Call it BR4 if you wish. So and look at this region from W to S3. Call it C. So now the key observation: this domain, this cobordism Z, if you equip it with the standard symplectic structure, this is indeed a strong cobordism. Okay. Okay. So now once we have this, there is a result of Echeverria, which says that then such a cobordism indeed has some sort of neutrality property, but in monopole Floer homology. This is the key point where we have to use monopole Floer homology. This result is completely unclear that whether it will exist in the Hegar-Floer setting. And I mentioned that okay, this result was announced in some ways maybe some 20 years ago by Morocco and Rollin, but the exact details never kind of appeared anywhere. So but now we have a full result, and that is due to Echeverria. So now once we have this result, then just kind of some simple structure of the monopole homology for S3 tells you the result in that theorem. So we want to work with the Hegel homology instead of the monopole homology because it has much, much more friendly for computation result friendly kind of the structure, and luckily result of Colon, Gijini, Honda or Kutluhan, Lee, Taubes says that we can go from the monopole homology to Hegel homology. Contact classes are matched, so everything will be fine. Okay, so this is the bit kind of just a summary of the first theorem. So now our goal becomes the following one. So then for any fitable contact structure psi on a Briskon homosphere, our goal will to prove that in this is contact class failed to satisfy the condition in the previous slide. So if we show that, then no contact type hypersurface embedding or no racially convex embedding. So now a naive approach to will be that, okay, try to understand contact structure on Briskon spheres. But the fact that is, okay, that's very complicated. So on Briskon sphere, typically there will be many different contact structures. And indeed, if this number of the singular fibers grows becomes more than 3, you have incompressible tori. So then you have infinitely many contact structures. Although, some of this infiniteness comes from the Drew torsion, they are not fillable, but this could happen in many ways. So it's really complicated. We have a different strategy. We will use some further internal structure of Hegel homology and not homology. So for that, let me remind you this. As I said, this HF plus of y, this has this kind of what's called the tower part, which is essentially you have this tower part, you're basically typically Z2. It goes like this. And then here you have this kind of the final dimensional piece. This is HF reduced. Now what happens is that, okay, this kind of the tower is actually equipped with an endomorphism, so-called U. And what we know is that, first of all, the contact class always lies in the kernel of U. And I'm sorry, I will move to the next slide and we will lose this, whatever I try to write here. Sorry for that. So contact class always lies in the kernel of U. And moreover, this kind of the bottom generator, the generator for this bottom, I don't know, group is that so-called the theta plus, and then if you have a contact type embedding, just putting together this result, it has to be that, okay, contact class is indeed that generator. Okay, so now our goal will be the following one. Our strategy is that first remember the following one. If you are given a class in HF plus, this gives rise to a not invariant, so-called this tau xyk. If you take k to be a not in S3, this is famous to know the tau invariant, first introduced independently by Ojwa-Szabo and Rasmussen. So then our goal will be that. So on one side we have the contact class, on the other side we have this theta class. So what we're gonna do, we will find a knot in this Briskon homosphere for which the tau, this not invariant coming from the class C psi and class theta plus are actually different. So that will tell us that indeed this should be different, in particular no contact type embedding. Okay, this is the strategy, finding this knot with these properties. Okay, how do you do that? So, well, so the goal will be that, okay, we will look at the difference of this and we will try to show that that is kind of strictly positive. Okay, so now I will look at individually finding an upper bound on the let's say, if you wish, let's call this contact tau, the one on the left, and the one on the right, let's call it smooth tau. So what we're gonna do, we'll find an upper bound on the contact tau, and we'll find a lower bound on the smooth tau. So first of all, what is our knot? Our knot will be this. If I draw my Briskon sphere as like this, so this is A1 over A1 prime, all the way to AN over AN prime, where this A1 prime through AN prime has to obey a certain equation. So this is 0. So what will be my knot? It will be just a regular fiber of this Ciphered fiber picture. This is my K. Okay. So now for the contact tau, is that there is this kind of result by Hedden, is that if k happens to Legendre, then there is an upper bound on the Tosun-Banach number of k. So in our case, we are thinking some Ciphered fiber spaces. We would like to replace this TB with the so-called the twisting number of the this regular fiber. So this is, instead of the measuring contact framing with respect to Ciphered framing, we would like to measure contact framing with respect to Ciphered framing or fiber framing. So you do that, and you get an upper bound okay, you get a lower bound for the contact tau in terms of the twisting number. Okay.
So, yes. The tau that you're talking about here, that's related to TB, does that agree with the tau on your previous slide in the case that your 3 manifold is S3?
It does.
Okay.
Yeah. Yes, in the case of S3, there is no smooth tau. There is no. It's just the one.
Okay.
Yeah.
Thanks.
Welcome. Good question. So, okay, so this was the kind of how you find lower bound on contact tau from this result of Hedden. Okay, and recent results of Catherine Rao and then results of Catherine with Matt Hedden also gives a way to kind of get an estimate for the smooth tau. And it is this theorem. So whenever you have a negative definite form manifold, negative definite form manifold filling of y, and k is some not in there, then this is the kind of the result, namely for any smooth surface sigma in X with boundary k, you have this kind of adjunction equality, this version of adjunction equality available. And here, just one thing is that this T is a kind of the, let's say, particularly nice spin-C structure, so-called the sharp spin-C structure. And what is that? It essentially says that if you puncture this negative definite thing, look at the cobordism, and the degree of the spin-C structure should be the equal to of the D invariant. It's just kind of the, let's say, a nice spin-C structure. So in the case we are considering, in our case, k is actually a slice in a negative definite plumbing, and this negative definite plumbing of Briscoe spheres is this star-shaped graph, which is negative definite, and k indeed will be sliced in that negative definite plumbing. So so this theorem good, then we have to go understand each of these term. There are some non-trivial calculation, but you can do it, and then you can find that. So after calculating all this, if you just look at the difference of the contact tau and smooth tau, you find that it will have such a lower bound. Okay, so and the lower bound is completely in terms of the parameters a1 through an and the twisting number. So now the only thing we need is that we need to prove, okay, this upper bound, this lower bound is indeed strictly positive, and that is the next theorem, where indeed for any contact structure, not necessarily fillable, not necessarily even kind of tight, for any contact structure on Briscoe sphere, we can give a uniform lower bound on the twisting number, and it is this quantity. So often this lower bound, if you look at some, let's say, particular class of Briscoe spheres, in particular if you focus on the fillable ones, you can typically kind of get much improved lower bound. You can get it actually quite close to, let's say, 0. But the point is that, okay, it is hard to do this kind of thing, like if you just consider general Briscoe spheres. Here, again, regardless of a number of singular fibers, you get this uniform lower bound, and it is good enough for our purpose. And putting this together is the last point of the proof. So now, in my remaining time, I'd like to make some final remarks. If you will remember, in my first slide, I talked about, or I mentioned that we will talk about Stein domains in various degree of convexity. We talked about holomorphically convex one. These are the one that, just maybe most topological, like just tiny bit like, control on topology and framing of two-handle is good enough. But then the next was rational convexity, there is one other notion of convexity, is the so-called the polynomial convexity. So, and this is also very similar to rational convexity type of domains that's studied in complex function theory, where on such domains, any holomorphic function is indeed uniformly approximated by polynomial functions. So we have a kind of a criteria when a domain in CM is indeed polynomially convex. If you will remember, in the case of holomorphically convex domain, we only had some J-convex function in the neighborhood of the domain. And the only thing this homomorphic convex domain was remembering from CM was the complex structure. That was the only thing. But rational convexity was the domain that it wasn't just the complex structure, but it also was saying that indeed the induced Kähler form extends to some Kähler form on CM. In the case of polynomial convexity, what happens, what this characterization says that, okay, it says that indeed you also have some control on the J-convex function itself. So, so this characterization of Oka in particular can be used to show that if you have a polynomial convex domain in CM, indeed you can, you know, by attaching only handles of, let's say in the case of C2, only handles of index 1 and 2 to reach 4 balls. So in other words, this cobordism I was talking about earlier in the case of rational convexity, indeed that's actually a Weinstein cobordism. So this notion of polynomial convexity is also studied by Eliashberg and Silibak in the same paper, where they prove holomorphic convexity and rational convexity are same, essentially equivalent in complex dimension 3 and above, and where they study polynomial convexity. They have very useful, very nice, you know, criteria to recognize a polynomial convex domain. But in particular, they have the following conjecture, where they say that if you have a simply connected polynomial convex domain, and then it has to be subcritical. They come very close to proving this, but not quite. And indeed, for m is equal to 2, at least Yasha claims that this is possibly true even for non-simply connected domains as well. And just to kind of emphasize on this simply connected part, in the same paper, indeed, Silibak and Eliashberg, for any in complex dimension 3 and above, they find non-simply connected polynomial convex domains which are not subcritical. So it's really interesting, you know, just some symplectic geometry, but on the other side, some kind of building on some example already in Hatcher's book and showing that why it cannot be subcritical. So what I would like to say here is that just a remark that we indeed can verify this conjecture of, let's say, weak form of Silibak, form of conjecture by Silibak and Eliashberg. Namely, if you are given a polynomial convex domain in C2, if it is simply connected, or if the boundary is rational homosphere, then indeed such a domain has to be just a 4 balls, and in particular boundary has to be S3. So just a kind of comment, and I think it is possible that we haven't yet verified, but maybe a little bit better understanding of just possibly it will be true that, okay, indeed we can just do this for any domain in C2. Okay, so I guess one last slide I have is that I want to just kind of maybe talk about some further questions that could be related to what I said. So as you will remember, I talked about that essentially if you focus on geometric homology spheres, there are the Ciphered fiber space ones, then if you choose the correct orientation, they never embed as contact type hypersurfaces. And this so-called WNs I mentioned, that infinite family of contractible manifolds, boundary of those are all hyperbolic, and they also can never embed as a contact type hypersurface. So, and indeed, we don't know any example of a rational homogeneous sphere besides S3 that embeds in R4 as a contact type hypersurface. And just a question, do they exist? And the conjecture of Wei-Min Chen says no. Maybe motivated more like maybe more holomorphic curve techniques, or kind of the maybe intuition that he thinks the answer is no. It's an open question. So, and of course, the other thing is that one might be interested is that what happens if you think about contact type embeddings in other manifolds, for example, CP2. So another question is that, of course, we can be interested asking all these, various domains in Steiner manifolds other than C, and you can ask the same questions. So, and maybe Eliashberg-Stilipak's paper could be useful for this question. And I mentioned about that kind of earlier when I drew that diagram. We had rationally convex one. They're always contact hypersurfaces, their boundaries, or they are homomorphically convex. So one question is that how this symplectic convexity and pseudo-convexity are related. The example I gave earlier, the corollary, was saying that you cannot go from pseudo-convex to contact type hypersurfaces. We don't know about the other direction, but in general, that is something that we don't know everything there. So there are some kind of certain arrows. It is unclear whether you can reverse them or not. Finally, as I said, like this kind of what we try to do here, just kind of made it clear that this kind of Liouville versus Stein cobordism in dimension 4 is really important for this question. So essentially, what our result proves, if you put together our results in kind of rational convexity case and polynomial convexity case, it says that the distinction between polynomial convexity and rational convexity is equivalent to the distinction between Liouville versus Stein cobordism. Or yeah, and maybe one last question. We still don't know the full answer to Gomp's problem. So whether, remember, it was saying that there cannot be pseudo-convex embeddings for Briscoe spheres with either orientation. And I think with that, that's all I want to say. Thank you so much.
All right, let's thank Bulent. Are there any questions? I have a question. When you were explaining how to distinguish the contact invariant from that theta plus, kind of at the end, it boiled down to saying, like, for any contact structure, the twisting number is, yes, sufficiently large. So is that true for both tight and over twisted contact structures?
It is true. It is true. Indeed, when you have over-twist contact structure, maybe, I mean, again, for this question, it will be completely not relevant. Even like tight non-fillable ones will be irrelevant for this question. But I mean, if you have an over-twist contact structure, you can make twisting arbitrarily big. Yeah, so really, I mean, when we were saying for any contact structure, I think we meant like tight ones or like fillable ones, but it really doesn't matter if you think over-twist one as well.
And can you say maybe a couple of words about how you show that without really knowing anything about the contact structure?
Yeah. So okay, so well, I mean, so what goes in the proof of here is kind of you try to implement usual convex surface theory argument, which is that this Briscoe homosphere has a structure of Ciphered hyperspaces. It's sorry, I think I just need to, something happened. So can you still hear me, Laura? Okay. So so it has this sigma has a structure of Ciphered hyperspace. It has n singular fibers, and typical idea is that you try to kind of I guess you start with kind of assuming the twisting number is a certain quantity, let's say T. And then that means there is some regular fiber which you can make it to the general, and the twisting of this regular fiber with respect to any given contact structure is T, okay, the contact structure at hand you have. And your goal is then to kind of see what kind of the twistings are available for this. So, and then what happens is that, okay, so you have this kind of the splitting of your Briscoe homosphere into n singular fibers, which you can take them as disjoint, and each of them as, like, topologically just a solid torus, and you can make them so that they are some convex neighborhood of the singular fibers, which you can make them Legendre. And then you have complementary piece, which is S1 cross some a sphere punctured n times. And what happens is that you play this game is that by kind of considering various annuli between this kind of the singular neighborhoods or this neighborhoods, and try to kind of thicken them as much as you can, so that if there are any bypasses around, they are hanging around, which help you to increase the twisting number. So and what we did is essentially just kind of to play this in an organized way. In particular, we introduced a very useful lemma, which is, if you have thought about it a little bit, you'll remember this twist number lemma, or maybe I guess the bypass various result that Kohonda and others introduced. Here, what we kind of developed is, okay, there is some sort of I guess what we call it, Tom, in our paper, we call it congruence principle. So somehow there is kind of some ways that, okay, and maybe a nice structure of Briscoe spheres allows you to do this. So it's a bit involved, but not too bad, not too bad. I'll say convex surface theory goes into proof.
Cool, thanks. Are there other questions for Bulent?